The root-locus method applied to control engineering. Hello everyone. In this video, we're going to talk about the root-locus method applied to control engineering, and to do so, we're going to solve 4 exercises with increasing difficulty. Let's go to the first exercise. Exercise 1 said that for a system with g of s equal to k over s times s plus 2, what is the value of k for which one of the closed loop complex conjugate poles lies at s equal to minus 1 plus j10? Okay, my friends, this is the exercise. Let's go to the solution. By plotting the poles, we find this. We have a pole at 0, we have a pole at negative 2, and as the exercise wants, we're going to have a pole at negative 1, j10. Observe that this distance here from the pole to the origin is the square root of 10 squared plus negative 1 squared, which is the square root of 101. The gain at the given pole is the product of the lengths from the poles divided by the product of the lengths from the zeros, which means that the gain is going to be k is equal to the square root of 101 times the square root of 101, which is 101. For this value of k, we have a pole at s equal to negative 1 plus j10. Okay, my friends, this is everything for exercise 1. Let's go to exercise 2. Exercise 2 says that given g of s equal to k over s times s plus 4 times s plus 15, find the dominant poles for a maximum overshoot of 30%. Okay, my friends, this is the question. Let's go to the solution. Using the expression for the maximum overshoot, we obtain that minus pi times zeta over the square root of 1 minus zeta squared has to be equal to 0.3. Okay? We wish a maximum overshoot of 30%. And applying the natural logarithm to both sides, we get minus pi times zeta over the square root of 1 minus zeta squared is equal to minus 1.2. From this, we get that zeta is equal to 0.357. And the undamped natural frequency can be calculated using Raph's array. Let's work on the characteristic equation of this system. The characteristic equation is s times s plus 4 times s plus 15 plus k equal to 0, or s cubed plus 19 s squared plus 60s plus k equal to 0. And the Ralph's array becomes s cubed, s squared, s1, and s to 0. And here, a0, a2, a1, a3, b1, and c1. From this, we know that a0 is 1, a1 is 19, a2 is 60, and a3 is k. Then let's substitute. One, 19, 60, and k. B1 is equal to 140 minus k divided by 19. And by making B1 equal to 0, we get that k, if B1 is equal to 0, we get that k is equal to 1140. K equal to 1140. All right? Why did we do this? We are going to use this here, this row here, to find what we want. Okay? The poles. And 19s plus 1140 equal to 0, where s is equal to plus minus j 7.74. All right. I'm going to erase it here for more room. This is an auxiliary equation. By making B1, we find k equal to 1140. In making use of the auxiliary equation for the term s squared, we find that s is equal to plus minus j 7.74. All right? With zeta equal to 0.357 and Wn, the undamped natural frequency, equal to 7.74, the dominant pair of poles will be at negative zeta Wn plus minus j Wn, the square root of 1 minus zeta squared. Okay, this is the location of the poles for a maximum overshoot of 30%, which is equal to minus 2.75 plus minus j 7.24. This is the response of exercise 2. Okay, my friends, this is all for exercise 2. Let's go now to exercise 3. Now let's go to exercise 3. Exercise 3 asks us the number of breakaway points in the root locus plot of the system represented by this block diagram. Okay, my friends, this is the question. Let's go to the solution. To find the breakaway points, it is necessary to come up with the transfer function and work on the characteristic equation. The transfer function is going to be C of S over R of S equal to K over S plus 20 S squared plus S plus 4 divided by 1 plus K S plus 20 S squared plus S plus 4. Okay? This is the transfer function. And if we develop this, we get that the transfer function is K over S plus 20 times S squared plus S plus 4 plus K. This is the transfer function. We are going to work on the characteristic equation. The characteristic equation is the denominator of the transfer function equal to 0. It is then going to be, if we develop this multiplication, we get S cubed plus 21S squared plus 24S plus 80 plus K equal to 0. To find the breakaway points, we need to write K in terms of S. Like this, K is then equal to minus S cubed plus 21S squared plus 24S plus 80. And to find the breakaway points, we need to differentiate K with respect to S and equal it to 0. Then the derivative of K with respect to S has to be equal to 0. Okay? When this happens, we have the breakaway points. And this is equal to minus 3S squared minus 42S minus 24 equal to 0. And the roots of this equation are S equal to minus 13.4 and S equal to minus 0.59. All right. These are the solution of this equation, the derivative of K with respect to S, that gives us the breakaway points. Now, the root locus on the real axis will be S equal to minus 20. Okay, this is one of the open loop poles. The other open loop poles will be S equal to minus 0.5 plus minus J 1.94. These complex conjugate open loop poles are the roots of this equation, and S equal to minus 20 is the root of this equation here. Okay? Now we need to assess whether they are part, if the breakaway points lie in the root locus along the real axis. We're going to choose a test point. For any test point S on the real axis, the sum of the angular contributions of a pair of complex conjugate poles is 360 degrees. Thus, the location of the root locus is determined by the other pole, that is s equal to minus 20. Okay? So the contributions of this will be 360 degrees, and they will not help us decide whether or not these are breakaway points. We need to concentrate on this, negative 20. The range from minus 20 to minus infinity is part of the root locus on the real axis. We have the complex plane here. Here is sigma, here is JW, okay? And here we have minus 20. This is one of the open loop poles. The root locus on the real axis will be from minus 20 all the way to negative infinity. This part here, from 0 to minus 20, does not belong to the root locus of the system described by this block diagram. Since minus 13.4 and minus 0.59, since these values here do not belong to the portion from minus 20 to minus infinity, we understand that they don't belong to the root locus. They are not, therefore, breakaway points. Okay? Since minus 13.4 is here and minus 0.59 is here, they do not belong to the root locus. The root locus is only from minus 20 to minus infinity. Then we understand that these are not breakaway points. So the solution of this equation that theoretically would give us the breakaway points they don't belong to the root locus, therefore they are not breakaway points. Okay, my friends, this is everything for exercise 3. Let's go now to exercise 4. Now let's go to exercise 4. Exercise 4 wants us to draw the root locus plot of the system represented by this block diagram, and also exercise 4 wants us to determine the value of k such that the damping ratio zeta is 0.5 for a pair of dominant complex conjugate closed loop poles. Okay, my friends, this is the question. Let's solve it. Let's go to the solution. Firstly, we have to analyze the magnitude condition and the angle condition based on this block diagram. The angle condition is going to be that the angle of k over s plus 1, s plus 2, this angle, which is equal to the negative of the angle of s minus the angle of s plus 1 minus the angle of s plus 2, has to be equal to plus minus 180 degrees to k plus 1. Okay? This is the angle condition. Now let's go to the magnitude condition. The magnitude condition The magnitude condition is that the magnitude of k over s, s plus 1, s plus 2, the magnitude of this has to be equal to 1. Okay? These are the conditions. This is the angle condition, and this is the magnitude condition. Now let's go over the procedures for sketching the root locus. Number 1, determine the root loci on the real axis. This is going to be number 1. Root loci on the real axis. The first step is to locate the open loop poles. Let's see which are the open loop poles. We have 3 open loop poles here, s equal to 0, this open loop pole, s equal to -1, this open loop pole, and s equal to -2, this open loop pole. Next, we use a test point to determine the root loci on the real axis. Okay, let's use a test point on the positive real axis. Test point on the positive real axis. Where is the positive real axis? You have the complex plane here. Okay. Remember that S is equal to sigma plus JW. Here is JW and here is sigma. The positive real axis is this part here, from 0 to positive infinity. If we take a test point on the positive real axis, we find that the angle of S is equal to the angle of S plus 1, which is equal to the angle of S plus 2, which is equal to 0 degrees. We see that the angle condition is not satisfied. And the conclusion is that there is no root locus on the positive real axis. Now let's take a test point on the negative real axis between 0 and 1. Between 0 and 1 here, zero and -1. Between 0 and -1, we're going to use a test point between 0 and -1. What is going to be the conclusion? the angle of S is 180 degrees, and the angles of S plus 1 and S plus 2 are 0 degrees. And in accordance with the angle condition, we verify that it is satisfied, because minus the angle of S minus the angle of S plus 1 minus the angle of S plus 2 is equal to minus 180 degrees. And thus, we conclude that the angle condition is indeed satisfied. Okay? Now, let's place a test point between -1 and -2. Okay? From -1 to -2. And we're gonna see that the angle of S here is equal to the angle of S plus 1, which is 180 degrees. And the angle of S plus 2 is equal to 0 degrees. What can we conclude from this? We conclude that the angle condition is not satisfied. Why? Because the negative of the angle of S minus the angle of S plus 1 minus the angle of S plus 2 will be equal to negative 360 degrees. And negative 360 degrees does not satisfy the angle condition. Then the segment between -1 and -2 does not belong to the root locus. To finish, let's use another test point. Now let's use a test point from -2 to -infinity. Okay? We are going to use this test point and see whether this portion of the real axis belongs to the root locus. Here we see that the angle of S is equal to the angle of S plus 1, which is equal to the angle of S plus 2, and they are equal to they are equal to 180 degrees positive. 180 degrees positive. And if we do this, the negative of S minus S plus 1 minus the angle of S plus 2, they are equal to negative 540 degrees, and negative 540 degrees does satisfy the angle condition, and we can infer that that this portion from -2 to -infinity is indeed part of the root locus on the real axis. Okay? Now let's go to the second procedure. Okay? From this, let's go to the second procedure. The second procedure will be to determine the asymptotes of the root loci. Second procedure, to determine the asymptotes If a test point is selected very far from the origin, the approximation is possible. We are going to work with the following approximation. The limit of s going to infinity of k s plus 1, s plus 2 is equal to the limit when s goes to infinity of k over s cubed. Okay? If we select a point very far from the origin, this approximation can be done. And the angle condition becomes, see that we need to work with the angle condition all the times. The angle condition becomes that -3 times the angle of s will be equal to plus minus 180 degrees to k plus 1. Or the angle of asymptotes will be plus minus 180 degrees to k plus 1 divided by 3. And we choose 60 degrees, -60 degrees, and 180 degrees. These are the angles that we choose. Okay? To draw the asymptotes, now let's see how we draw the asymptotes. To draw the asymptotes, we must find the point where they intersect the real axis. Again, we are going to place a test point very far from the origin. If we do this, then we can conduct the following approximation, which is going to be approximately equal to k over s plus 1 cubed. By doing this, we are going to assess the angle condition of this. The angle condition k over s plus 1 cubed has to be equal to plus minus 180 degrees to k plus 1. Okay? A root locus given by this equation consists of 3 straight lines. Okay? So, minus 3, the angle of s plus 1, equal to plus minus 180 degrees to k plus 1, which leads to the angle of s plus 1 equal to plus minus 60 degrees to k plus 1. Now, if we substitute again s by sigma plus jw, we get that sigma plus jw plus 1 equal to plus minus 60 degrees to k plus 1. Okay? And now we're going to find the asymptotes. We're going to take the tangent. So the inverse tangent of w over sigma plus 1 will be the angles of 60 degrees, minus 60 degrees, and 0. And from this, we get three asymptotes. The first asymptote will be, I'm going to draw them here. The inverse tangent of this is 60 degrees, minus 60 degrees, and 0. I'm going to draw them here, the asymptotes, for you to see. And then we have here JW, and here sigma, here -1, this goes like this goes like this is j square root of 3, and here minus j square root of 3. Okay, this line here is w equal to 0. This one here is sigma plus 1 minus w over the square root of 3 equal to 0. And the lower one will be sigma plus 1 plus w over the square root of 3 equal to 0. So these are the asymptotes in accordance with our calculation. Okay? Following this, we can determine the asymptotes. And they meet at s equal to -1. Or if you prefer, sigma equal to -1. Now let's go to the third procedure, to the third step in determining the root locus. Now we are going to determine the breakaway points. Number 3. The breakaway points. Let's determine the breakaway points. The breakaway point is where the root locus branches originating from the poles at 0 and -1 break away from the real axis and move to the complex plane as k is increased. They can be determined from the roots of the equation. We are going to differentiate k with respect to s and equal it to 0. This is how we find the breakaway points. In this exercise, the characteristic equation is given by k over s, s plus 1, s plus 2, plus 1 equal to 0. And if we develop this, we get that k is equal to minus s cubed plus 3s squared plus 2s. And if we differentiate k with respect to s, we get that dk ds is equal to minus 3s squared plus 6s plus 2, and this has to be equal to 0. All right? And the roots of this equation are s equal to minus 0.4226 and s equal to minus 1.5774. Okay? Since the breakaway point must lie between 0 and 1, as we saw, the breakaway points have to be along the root locus or at the root locus, and only the portion from 0 to 1 belong to the root locus on the real axis, then only s equal to 0.4226 is a breakaway point. S equal to minus 1.5774 is not a breakaway point. Only this is a breakaway point because it has to be along the portion from 0 to 1. Okay? So the only breakaway point is this. After this, we go to the fourth step, which is to determine the points where the root loci cross the imaginary axis. Let's go now to the fourth step. The fourth step, determine the points where the root loci cross the imaginary axis. Okay? This is the fourth step. And to do this, we are going to use Rao's stability criterion. From Rao's stability criterion, we have this array of terms, s cubed, s squared, s to 1, and s to 0. And here we have, remember that the characteristic equation, we have to fill this table with the characteristic equation, and the terms of the characteristic equation are s cubed plus 3s squared plus 2s plus k equal to 0. This is the characteristic equation. It can be easily found by working on this block diagram. and finding C of S over R of S. And this is the characteristic equation, and we're going to fill the array of terms like this: 1, 2, 3, K, B1, and C1. Okay? Where B1 is equal to 2 times 3 minus 1 times K over 3, which is 6 minus K divided by 3. And C1 is equal to K. Okay? And for the S21 term to be 0, for this term here to be 0, B1 to be 0, K has to be equal to 6. For B1 to be 0, K has to be 6. Alright? And now, the crossing point can be determined by the auxiliary equation obtained from the S2 row. We are going to use this row here. We are going to create an auxiliary equation from this row with the value of K that we found equal to 6. And the auxiliary equation is 3 times S squared plus K has to be equal to 0. Okay, since K is 6, we get that S is equal to plus minus J square root of. And by following this procedure, we discovered that the frequencies at the crossing points on the imaginary axis are W equal to plus minus square root of 2 for K equal to 6. Okay, for a gain equal to 6. And with this, we have everything to draw the root locus. The root locus is going to therefore be, this is the real axis, this is the imaginary axis. We have root locus from this pole to this pole. We have an open loop pole at 0, another at -1, and another at -2. We have root locus here, and we have root locus here. Okay? And the other part of the root locus is this. Alright? This is the other part of the root locus. We have root locus from -2 to -infinity. We have root locus here, and we have root locus in this part here. Okay? And if we increase the gain, K equal to infinity, the graph goes to that direction. Now, to finish, the exercise wants us to find a pair of dominant closed loop conjugate loop poles for 0 equal to 0.5. Okay, so the complex conjugate closed loop poles for 0 equal to 0.5, and we're going to find it like this. Observe that plus minus the inverse cosine of 0 will be equal to plus minus the inverse cosine of 0.5, which is equal to plus or minus 60 degrees. Okay? And they make 60 degrees with the negative real axis, like this. 60 degrees here, 60 degrees here. And then at the crossing, we have the point we wish for k, and we want to find the value of k for that point, where 0 is 0.5. You're going to find it like this, okay? By looking at the graph, we say that S1 is minus 0.3337 plus J, 0.5780, and S2 equal to minus 0.3337 minus J, 0.5780. The value of K that produces such poles is found from the magnitude condition. We are going to find the value of K for such poles using the magnitude condition, and the magnitude condition leads us to K equal to S plus 1, S plus 2, for an S equal to negative 0.3337 plus J, 0.5780, and this gives a value of 1.0383. Okay, so the value of the gain here is 1.0383. Okay, my friends, this is everything related to the root-locus method applied to control engineering. This is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!